Chapter 10, Problem 28. Calculate the moment of inertia of a thin plate in the shape of a right triangle about an axis that passes through one end of the hypotenuse and is parallel to the opposite leg of the triangle, as in figure P10.28a. Let M represent the mass of the triangle and L the length of the base of the triangle perpendicular to the axis of rotation. Let H represent the height of the triangle and W the thickness of the plate, much smaller than L or H. Do the calculation in either or both of the following ways, as your instructor assigns. Please note I will only be doing A. A. Use equation 10.17. Let an element of mass consist of a vertical ribbon within the triangle of width dx, height y, and thickness w. With x representing the location of the ribbon, show that y is equal to hx over L. Show that the density of the material is given by ρ equals 2m over LHW. Show that the mass of the ribbon is dm equals ρyw dx equals 2mx dx over L squared. Proceed to use equation 10.17 to calculate the moment of inertia. Okay, let's jump right into this. Chapter 10, Problem 28. Let's look first at what we're given. Obviously, we're given a triangle of height h, length L, mass m, and width w, where w is far less than h or L. It's rotating around an axis here. What do we need to find? Well, given our triangle, we imagine a ribbon of height y and distance from the point of the triangle of x. We need to prove that y is equal to hx over L, that the density of the material, ρ, is 2m over LHW, and that the mass of the ribbon is ρyw dx, which is equal to 2mx dx L squared. And after all that, we're supposed to find the moment of inertia. Okay. Looking at our triangle, we see that these are similar triangles. They both share the same angle, and they're both right triangles. Therefore, we can draw the conclusion: the ratio of h to L is the same as y to x. Rearranging to solve for y, we get y is equal to hx over L. Now, the next thing we need to show is that ρ is equal to 2m over LWH. So if we look at our triangle, and this time we include the width because it is a thin plate, we recognize that ρ, density, is equal to mass per unit volume, or mass divided by volume. So since this is a prism, the volume of this thin plate is going to be the area of the triangle times its width. Now the area of the triangle is obviously 1/2 base times height, which is 1/2 h times L. Multiplied by width, we get a volume of 1/2 HLW. So, since ρ is mass divided by volume, it's going to be equal to mass divided by 1/2 LWH. Simplifying, that goes to ρ is equal to 2m over LWH. Okay, next we need to show that the differential of mass, the mass of the ribbon, is equal to ρ times y times w times dx. If we look at our triangle, we see two things. One, our differential is x, height is y, and width is w. And we know that the differential of mass is going to be ρ times the differential of volume. Now we use these things, and since it's a prism, we say the differential of volume is going to be y times w times dx. Plugging that back in, we get dm equals ρy w dx. However, we don't stop there. Knowing this, which we just solved for, and knowing that ρ is equal to 2m over LHW, we can substitute this in for rho and find dm is equal to 2m times y times dx over LHW. Obviously, these w's cancel, which means we can rewrite it as 2my dx over LH. So this next bit requires a bit of creativity. We solved earlier that y is equal to hx over L, which means we can rewrite L as hx over y. Now if we go back to what we just found, where dm is equal to 2my dx over LH, we can multiply both the numerator and denominator by L, except use the substitution, which means we write 2my dx over LH times hx over y, which is L, divided by L, which means this whole term is 1. Obviously, the h's cancel and the y's cancel, and we're left with dm is equal to 2mx dx over L squared. Now the last bit, moment of inertia. The definition of moment of inertia is I is equal to integral r squared dm. Now, obviously, we're going to be integrating from 0 to L, since that's the length of our triangle. R is x, since that's the radius from our axis of rotation. And we solved for dm as being 2mx dx over L squared, which leaves us with this as our expression for moment of inertia. If we pull out the constants and combine like terms, we're left with 2m over L squared times the integral from 0 to L of x cubed dx. Now all we have to do now is integrate that. We get I is equal to 2m over L squared times L to the 4th over 4. Which, if we simplify, leaves ml squared over 2. Final answer.